One characteristic of correlation that I really like is that it's a fundamentally visual idea. And very quickly, I want to go through how to actually visualize a correlation. In other words, I want to go through the specifics of a scatter plot when you're comparing two continuous variables. So here's our first example. Suppose, and this kind of hopefully looks like an Excel sheet. Suppose we have two variables. We got, let's just call it X, and we have Y. And the assumption here is that for each row, we have kind of a subject on which we've made one type of measurement and another type of measurement. Okay, so maybe we're looking at the length and the width of the pinky toe. So each row would be a person, and this might be the width of their pinky toe, and this might be the length of their pinky toe. And we kind of look at this moving down through the data set. So how do we visualize a comparison of two variables like this? The basic idea is to just collapse each row into an ordered pair, an XY pair. So we're just going to pair off the data by rows, and each one of those is now going to become the X and the Y coordinate for a point in space. So each row, which remember comes from a person or a subject, is associated now to a point in space. And so if we set up an XY axis like we've done in, say, pre-algebra or algebra, we can actually visualize each one of these points by just using our x-axis scale and our y-axis scale to plot their rough location. And this is what we call a scatter plot for two variables. Now, the nice thing about correlation, as I mentioned before, is it's a very visual idea. You can kind of see, you can almost feel that the data on the left-hand side, the scatter plot from the data on the left-hand side, seems to more closely hug some sort of imaginary line. Whereas over on the other side, the dots seem more spread out, even though if they are kind of generally following the line that I'm tracing out with my cursor here. Right? This gets interpreted via a statistic called the Pearson correlation coefficient. The Pearson correlation coefficient, we're going to use the notation little r, essentially tries to measure the strength and the direction of a correlation between two variables. And visually, what happens here is if your correlation coefficient is negative, it means your dots are following a negative sloping line. And you can see visually that both of these data sets have negative correlations because they both kind of, generally speaking, as you move to the right, the dots seem to trend downward. But in addition to this, whether you're going to be negative sloping or positive sloping, we also have a measure of strength. And what we mean by strength here is how closely do these dots follow that imaginary line? How tightly are they packed in a line, and how spread out are they? Now for the variables or the data set where we're very, very closely following a straight line, what we're going to see is a larger magnitude in our correlation coefficient. In other words, this thing, if you forget about the plus and the minus sign, is going to be bigger when the dots are following the line more closely. So in comparison from the left data set and the right data set, our magnitude would be bigger for the correlation coefficient on the left, and the magnitude would be smaller for the correlation coefficient on the right. And we can see this. Our magnitude is 0.892 versus a 0.387. So we have this very nice single statistic, something called the Pearson correlation coefficient, that not only tells us the direction of the relationship, right, negative versus positive, but also measures the strength or how tightly those values follow our straight line. So a couple of quick things that we want to note about Pearson's correlation coefficient. First of all, it always falls between -1 and 1. Values close to 1 indicates what we'll call a strong positive correlation. Positive tells us the direction. This means that the dots, typically speaking, are going to be following a positive sloped line. As one variable increases, so does the other one, generally speaking. The strong part means that it follows that line very closely. Unlike in our previous picture here, right? When you're closer to 1, as we can kind of see in magnitude, you're closer along that line as opposed to the values that are closer to 0. They seem more spread out. It's two-sided here, so we can also have strong relationships, meaning we very closely follow a line, but that relationship in terms of its direction is the opposite. It's a negative correlation, and these are going to be correlation coefficient values near -1. And essentially what that means is as one variable tends to increase, the other one tends to decrease. If you have correlation coefficient values very close to 0, we won't have a linear relationship between these variables. Okay, so our weaker relationships are going to be closer in the middle. And the analogy that I like to use for this is sort of a seesaw. Remember, if you kind of move towards the middle of a seesaw, you exert less influence over who's going to go up and down. If you want to influence who goes up and down, you have to move yourself farther out to the right. So the stronger positions are at the ends of the seesaw, the 1 and the -1. The weaker positions are right in the middle at 0. I'm going to show you two ways to compute this correlation coefficient. The first is using the actual formula. We take for each row of our data and we compute a z-score. We multiply those z-scores, sum them all up, and then average them out by dividing by n-1. So this is our first approach, and I want to go over this just once, just so we can review our fill-down formulas and start to practice a little bit for the final exam. And then I'm going to show you a shortcut for it. So let's continue on to an Excel example. We're going to go into our week 12 materials, and we're going to open up the week 12 day 2 Excel workbook, W12D2, and we're going to get started with our first example there. All right, here we are. We want to compute the Pearson correlation coefficient using the following formula. And fundamentally, again, I'm using this as an opportunity to sort of review some Excel techniques and stuff that you should know for the final exam. The first thing that we're going to have to do, here's our data, x, y. And first thing I want to show you how to do is plot the scatter plot, so we can take a look at sort of visually what kind of correlation coefficient we would expect. We do this in the usual way. You can just select all of your data. You could do a Command A here, or you could click and drag, or you could hold the Shift command, Shift and Control, and click over and then down from the top thing. However you want to grab all of your data. As usual, we're going to go into the Insert command and go and move over to our different types of charts. Now, right below our statistical charts, where we find our histogram and our box plots, you should see a little XY axis with different colored dots, and when you hover over it, it says XY scatter. This is what we want to choose, and we always want to pick, in this case, the first of the options, and it should just look like a bunch of different colored dots. So if we click this XY scatter, we'll get exactly what I had described in the slides previously. Each row, 44.016, 175.6, each row is corresponding to some sort of dot, right? And as you hover over, you can actually see the dots. So in this case, my first row is the dot that I'm currently hovering over. So here's our scatter plot, and we can see that just visually, it seems like these dots follow a line, and the line is positive sloping. So what we're kind of expecting to get here is a correlation coefficient that's pretty close to a +1. Positive because our imaginary line here is positive sloping, and close to 1 because there's not a lot of spread out. The nature of the dots isn't very spread out from that line, and they seem to hug the line pretty closely. Okay, so for the moment, I'm just going to kind of drop this down to the side. We'll bring that back later. I now want to focus on this particular equation. This is the definition of how we compute our Pearson's correlation coefficient. We'll see a shortcut in a second, but here's why I want to review it. First of all, it involves us finding the z-scores associated to all of our x measurements. We also need the z-scores associated to all of our y measurements. Then we need to take their product and sum them all up. This will give us the top, or the numerator, that we need for our correlation coefficient. Finally, we're going to divide by our sample size minus 1. And here we're going to define our sample size as the number of rows that's in our data set. So we're not going to count this and this as two separate samples because in a sense we're thinking about these as two measurements on the same subject. So the total number of rows is going to end up being our sample size. Let's start by just computing our z-scores. Now remember, the formula for a z-score typically speaking is measurement minus mean divided by our standard deviation. So when we're finding our z-scores for the x measurement, we need to know what our mean for the x is and what our standard deviation for the x is. And then each one of our data points in that first column correspond to our measurements. So pause the video and on your own, go through these first four computations. Find the mean for the x column, the mean for the y column, and the corresponding standard deviations.